It's great to be here at the wonderful ISTA conference. I hope everybody is having a great time and learning a lot of new and interesting things. In this talk, we are going to be talking about rendering and what it actually is. Because with the recent developments over the last 10 years and all the modern frameworks and libraries that we see in the JavaScript world, such as Angular and React, we started using rendering more and more about things that are not exactly rendering. So we'll see what it is and how we can utilize it to make our web pages perform much better so that we can actually get a better user experience. So this is the agenda for the talk. We'll see first what is rendering. We'll see what makes rendering fast or slow. And then we finish with some practical approaches how we can improve the rendering performance of our web application. So first of all, what is rendering? Can anybody give it a shot? Rendering? Rendering? OK, so this is a Wikipedia explanation for that. Rendering, or image synthesis, is the automatic process of generating photorealistic or non-photorealistic image. What basically this says is that the way you generate the actual visual that the user sees on the device, whether it's mobile or desktop or console or whatever is the target platform. For web development specifically, this means that this is the process that takes the HTML markup as plain text that we know in the documents that we are downloading through the internet, and converting it into the actual web page that the user sees. But then again, we get to another important question. Why is rendering performance so important? After all, rendering and performance are relative terms. Some people have different perceptions about what is fast or slow. And the actual thing that makes it very important is that over the last couple of years, Google actually changed the way they index web pages. And now, the actual visualization speed of the page is a factor in how are actually pages indexed and how they're presented to users. And this is not accidental. If there's one company in the world that knows what's important for internet users, that's Google. So we need to trust them. And the reason for this is that over the last several years, basically the attention span of users has decreased. And people don't wait for a ton of time to get the actual visual of the page. And they want some kind of a native-like experience from web pages. And therefore, we, as people developing software, we need to address that and make our web experience much more faster. So in order to make our pages faster, to render faster, we actually need to know in detail what happens under the hood, how the browsers take the HTML page and convert it to an image on the display of the users. So even though modern browsers are quite complex as applications, they are really a collection of multiple different libraries and technologies. And if you had a chance to look at the repository of a modern browser, you'll see gigabytes of source code. So you can imagine how much code goes into a simple web page browser. But essentially, modern browsers are actually comprised of three main things. A parser, which basically converts the plain text files into something as a dynamic structure inside of the memory of the device. Then a rendering engine, which converts this into actual visuals. And of course, the scripting engine, like V8 from Chakra or SpiderMonkey. So if we very quickly look at what happens when we load the page, we get this oversimplified diagram, which basically says that when we know the HTML file, it's being parsed. When the parser reaches some kind of CSS or JavaScript, it starts looking into it. And then the CSS and the HTML DOM are combined into a DOM tree, and it's displayed. Essentially, this is true, but it's, again, a bit oversimplified. So we'll dig into more internals, specifically for the rendering engines. We have Gecko in Mozilla, we have Chrome, for example, of course, in Chrome with Blink, and WebKit and WebCore for Safari. And what happens is that there is a thing called critical rendering path, which basically says the minimum possible steps that we need to take in order to have some kind of a meaningful paint to the actual user. And now we'll dig a bit even deeper into this. First, we'll see how the DOM tree is actually built. So first thing that happens when the parser starts looking into the HTML page is basically just looking at the different HTML tags and trying to build the DOM hierarchy of the elements. This happens in several stages. First, we have the bytes, which appear bytes, of course. Then we see them as characters, the actual strings that are forming the tags. Then the tags are converted into tokens that basically allow the browser to understand when one element starts, when the other ends, and based on that, to build a series of nodes. And inside of different tags, there are other tags, which allows the browser to understand the hierarchy of the different elements within the page. And at the very end, it basically builds the DOM tree. But the DOM tree is just a tree of elements. It shows the hierarchy. It doesn't show any styles or anything else. It's just the structure of the document. Next, of course, is actually to make the web page a bit more user-friendly with actual visuals and actual styles. And this is where the CSOM tree is created. Basically, for each element, styles are computed, because as you know, with cascading style sheets, we can have shared styles between different UI elements. And what you're actually seeing in the DevTools in modern browsers as computed styles are exactly this. Not the styles that were defined in various CSS styles, but what is actually computed for each and every UI element so that this is the actual final thing that's going to be shown to the user. When you combine the DOM tree and the CSOM tree, you start to get a new kind of tree, a render tree. This is the actual thing that's going to be rendered. But the styles and the DOM tree are not merely enough. You need something more. And we get to another tree, the layout tree. Basically, these are the top and left styles, the width and height that you see in your HTML elements. Actually, layout is one of the unique features of HTML. There are many other UI systems besides HTML, so don't be fooled by that. There are other UI systems in the world, and most of them actually do not have layout. For example, Adobe Flash didn't have layout. Silverlight had some form of layout. But what we have in the browsers is quite a unique feature. But it comes with a price, of course. And this unique feature requires a tree of its own. So for each and every element, again, we need to compute what are the exact sizes and positioning of the elements. And even though with the layout model, we can define where the different elements are positioned, like with top and left, and we know where's the 0, 0 of the browser window. There's actually a third dimension. It is which is in front of which. And there are two things that play here. The z-index, which you probably all know, it's very simple CSS style, and the layout model. And they together define where basically different elements are sitting in front of each other. And the layer model is actually something a bit more complex. You have the layer model in order to help you to improve the performance, actually. Because more often than not, you don't want to change the whole page. There might be some minor glitch or minor thing, for example, a counter or a clock or something that stays, for example, at the header of the page. You don't want to redraw the whole thing, just so that there's a small counter updating there. And for example, especially in modern technologies, if you take, for example, a 4K monitor and you have a user that has a 4K page, to draw a 4K texture is really quite an overkill. And the layer models actually allow you to have different parts of the HTML UI rendered independently. And we'll see more about this a bit further on. And again, a layer tree is built. And once we have all the trees created for different elements in memory in the device of the user, we can basically see that we have the DOM, which is the hierarchy, the structure of the web page. We have the styles. We know how they will look like. We have the layouts, and we know where they will be positioned and how big they will be. And we have the z-index, and we have the layering to know which is in front of which. So the only thing we need to do now is just to paint. So painting in modern browsers has evolved a lot. It used to be purely a CPU operation, which is kind of a blocker for many use cases. And the idea is that basically you have all the information from different trees combined and converted into the so-called paint records, which are basically instructions how the device would actually render the actual page. And in modern browsers, this is typically done in a separate library. For example, in Chrome, this is Kia. And you can see here just a simple example of what actually happens. So you have several UI elements. You can basically imagine that behind these drawing commands, there are divs, spans, and whatever. And for example, if we take the first rectangle in the code, the bool one, it basically says, draw me a rectangle with 0, 10, 10 from the 0, 0 coordinate space of the element, and make it with size 100 by 160 pixels. So these are basically the drawing commands that were created by the simple divs that we have, CSS styles, for example, top and left 10, 10, and width and height 100 by 160. And for all the different elements, similar drawing commands are ordered. And this is actually how the visual styles and the code of the HTML is created into a series of small images, bitmaps, essentially. If we dig into some more detail about how this happens, for example, in Skier, we'll see that it takes several stages. First, we have the initial path generation. Then you basically have the rasterization, which defines where actually there will be some pixels. You might have some kind of masking. It can be dynamic. It can be from an image. And then you have the shading that basically says how the different pixels would be colored. And at the end, the texture is transferred, and it's ready. And a series of textures that are related to the different layers that we generated are drawn as quads, and basically the last thing that needs to happen is just to combine them all into a single image. And this is the job of the compositor. It happens usually in a separate thread, and it heavily utilizes the GPU. Because actually, modern GPUs are quite powerful, and they're quite used to manipulating textures and calculating drawing commands. So modern browsers are using more and more the GPU. And it's not just for the compositing, it's same for the paint. Even though Skier can actually draw in a software mode, which basically is done on the CPU, it can at the same time do this on the GPU, and it has rendering backends for basically different platforms. So a lot of versatility there. And the additional benefit from that is that they can be executed in parallel, meaning that the CPU can do one thing and the GPU can do another. And in this example, we can basically see what's going on with the compositing. You have a stack of layers that are on top of each other, and they basically squashed into a single texture. And this is how the different layers are combined. And at the end, you see basically the complete page as a single image displayed on the browser. OK, so we got a basic idea about what's going on inside of the browser, what are the different steps that we take from the building of the DOM tree through the building of the CSOM tree, then the layout tree, then the layers tree, and finally getting to painting and compositing. Now we'll see a bit more about what are the different things that actually swallow the rendering. First of all, of course, CSS. It's not for free. Basically, some styles are cheaper, some styles are more expensive, but for example, border radius, box shadow, filter, they're quite expensive because they need to compute a lot of pixels around the pixel that is there, and it's really a thing that you should carefully consider before using if you are trying to achieve maximum performance for your web page. And child, of course, it's Sue selector, which is quite expensive, and of course, position fixed again because it basically messes up the whole layout. There are, of course, things that are render blocking. They're quite important to consider as well. For example, script tags that are in the head. So you should either defer them or use async or have them somewhere later, but they're essentially stopping the parser and making them store the whole rendering of the page. Style sheets are also render blocking. Don't be fooled, even though CSS is quite native to the browsers, it's essentially, again, render blocking. And also import tags. They're, again, render blocking. So another thing that's kind of a problem is layout by itself. As we said earlier in the talk, basically, not all UI systems have it, and it's quite expensive operation. Because with layout, you can basically have the whole page messed up by the styles of a single element. Because all the elements in the layout tree are related to each other, and they can have size and position that's defined by other elements. For example, when you're using percentage tags for the size or the position. And basically, whenever you change a layout style, the whole layout style needs to be recalculated and then painted and then composited. But enough about the expensive things. Let's talk about some things that are actually cheap to render. Transforms, like translate, scale, matrix, rotate, skew, they're actually cheap. And this is for a specific reason. Because if we go back to the way we talked, the pages are rendered, from the DOM tree, through the styles, from the layout, and the layers, at the very end of all this was the compositing. And if we can skip all the first steps in this workflow and we can just go to compositing, it will be much cheaper. And this is exactly what happens with transforms. Basically, nothing is recalculated as styles, nothing is re-layout. You just have the textures that were already painted, transformed. They're moved, their opacities changed, they're rotated, but it's quite cheaper to render, exactly because it's so later on in the rendering pipeline. And again, if we touch on layers, um, they're actually a performance problem and a performance solution at the same time. Because if you have like very small UI elements that are changing constantly and the whole of the rest of the UI screen is basically not changing, they're great because you can just paint everything to a separate layer, use the old texture for the background, and everything's fine. But once you get into many layers, they start to become a problem because when we talk about performance, it's directly related to the hardware. It's CPU time and GPU time. But when it comes to layers, it's not only that, but actually memory. And when you have a lot of different layers, they consume a lot of memory. And the pure resources that are needed to maintain different layers are actually quite a lot. So when you use layers, you need to reuse them with caution, not overuse them. And now we'll see some more practical approaches how we can basically improve the rendering performance of your web application. Of course, as with anything that's related to performance, less is more. This goes for everything basically, but it's very true for JavaScript itself. JavaScript is great and it has evolved a lot over the last 20 years. And modern JavaScript engines such as V8 and Chakra and SpiderMonkey have a ton of different optimizations how they can make the script actually run faster. That being said, JavaScript is still slow compared to native applications, and the actual accessing of the HTML DOM from JavaScript is actually a very expensive operation. You might not notice it in standard interactions with web pages because typically something that's in the milliseconds, you don't really notice it. It's something that's go by. But when there are thousands of different operations happening at the same time, JavaScript is actually becoming a problem. And it does in several ways. We kind of know very well the different approaches that JavaScript libraries and frameworks use. For example, the virtual DOM of React-like libraries, the change detection that we have in Angular. But the actual benefit and what they do in the background is that they try to minimize the different operations that they do in the actual HTML DOM. Because what we have in the frameworks and the libraries is basically, let me make a copy of the actual HTML. Let me manipulate it my way. And then only when I'm sure that I'm done and all the different operations that I want to do to the fake DOM are done, then let's update the actual page. And the point here is that you need to use this as an example, that you need to basically be cautious of the fact that every operation that you have from JavaScript to manipulate the actual DOM is very expensive. And you should be cautious to limit this as much as possible. And another important thing is how you read and write things in the DOM. Because if you are constantly reading and writing the same things, you might actually be spawning a lot of different restyle calculations, a lot of different layout calls. So you should be cautious when doing that. And another important thing about JavaScript libraries is that they don't come for free. They're great, they're awesome, but if you kind of look at a modern web app and all the libraries that a modern framework has and all the needed third-party libraries that you have for various reasons, for PDF file generation or for Excel file generations or whatever, you actually see that there is a humongous pack of things that you have that are supposed to be loaded when the user initially visits the page, which is kind of horrible for them because they, for example, just want to visit your page, and probably in your home page you have actually something that's quite simple, like, for example, 4 or 5 bullets and image and a header with several things. But in order to get all that, the users and their device, accordingly, have to take all that. And the thing about JavaScript resources is that it's not only that modern JavaScript libraries and frameworks have a lot of overhead for the thing that they're delivering. Don't get me wrong. Modern libraries and frameworks are great. They give us a lot of things. You have routing, you have components, you have a ton of useful features. But the truth is that it's kind of too much sometimes just for the initial user experience. And we can see here on the image what is the actual difference between downloading a JavaScript file and downloading a simple raster image. You can see they're both the same size, and from network-wise, they basically would take the same amount of time because they're just things that are transferred to a network, and there's no way to make them different if they're the same size. But as we can see, for JavaScript, we not only have the actual downloading, we have some more time in order to parse and compile the actual JavaScript. Time that is actually on the main thread, on the CPU, is blocking. And at the same time, we see that the image decoding that can happen in a separate thread, actually, it's taking like several milliseconds. And then just to paint it, it's, again, milliseconds. Well, the JavaScript code, after it's parsed and compiled, it has actually to spend some time into execution. And this is even a bigger problem for slower devices and slower internet users, because basically this makes the page unusable. Something that was relatively okay for modern computer with fast internet might take minutes to the user, and they're almost for sure going to abandon the page altogether, because it's not really fine to wait for minutes just to load the main things that you have in Angular or can do or whatever. Thankfully, there's a simple solution for that. There are actually multiple different approaches that you can address this, but a standard approach to this problem is the PRPL pattern, which basically says that if the user doesn't need to know all these things from the very start, all the different routes that you have in the application, all the different styles that are associated with these routes, all the different code and third-party libraries that are related to this, you don't have to force them into downloading them when they initially visit your web page. And basically, just push the core basic HTML component and maybe the core of the library that you're using either for components or for whatever else. And have, if possible, the CSS styles inline so that you really have a CSS that's minimal and needed for the home page. And then just lazy load everything else, all the different libraries, all the different routes that are not needed for the initial paint, and actually deliver a meaningful experience for the user from the start. Another important thing that we need to consider when building modern web page applications is the size of the DOM. Very often we use already pre-made components from design systems or from libraries that we lose track of the actual HTML elements that are being added automatically. But this is wrong. We should be always cautious of the fact that the more we have from the DOM, the slower the page gets. Because, for example, operations that are very common and thoroughly used in modern libraries are, for example, get element by ID. The more you have DOM elements, the slower this one gets. And this is just one example. Basically, the whole page becomes slower if you have more HTML elements. So whenever you are creating your page, make sure that you really need all these elements and you're not just overusing them because it's easy. The same goes for depth. Basically, the traversing of the DOM tree gets slower and more complex the more you have nested elements in your page. So whenever you're feeling like, let's refactor this and make some additional wrappers around it so that it's more easy to read and easy to do, this is generally fine, but you should be cautious of the fact that you shouldn't overdo it. You should always think that something more than 5 to 10 levels of nesting, it's way too much. And you should always be cautious of the fact that you need to improve the way you structure your components in order not to have very deep HTML DOM trees. Another thing that's nice to consider is how you do several different operations inside of your pages. Because as we probably all know, in HTML you can do the same thing like a million different ways. And very often, if it looks the same, we don't really care. We just take the first approach that works and go with it. But this is not really the best way to do it, because although it looks the same, it might be more expensive to render, which might ultimately lead to slower performance of your web application. And a simple example of this is when you use visibility hidden versus display none. Both actually hide the element, and it's invisible to the user. But what happens with visibility hidden is that it's just invisible to the user. The styles are computed, the layout is computed, actually something is about to be painted, so you don't get any performance benefit from actually hiding the element. But if you use display none, it is actually detached from the DOM tree. It's not calculated, it's not layout. And basically, it's much more performant way to hide elements. Another similar case where things look the same, but actually with different rendering cost, is when you're using transform versus layout. As we said earlier, you can move elements with transforms, and this is actually quite cheap because it happens on the compositor, and for the user it's all the same because they see the element being moved. But if you use the layouts in order to move the element with top and left or whatever, you force basically the layout for the whole page for nothing. So if you need to move elements that are small and just want to get the optimal performance, it's much more performant to use transforms. Another very oftenly used thing in modern web pages are SVGs, scalable vector graphics. In general, they're quite nice. They're very small in size. They load very fast. If you open one, you'll see that they have a XML-like structure very similar to HTML. And they have vector, which essentially means that they're pixel perfect on any screen resolution device. And this is in general true, but again, we should be cautious of the things we use for SVGs, because if you have a very complex SVG, it actually slows your rendering, because SVGs are rendered runtime. while normal images such as PNG and JPEG, they're just pre-rendered and decoded at runtime, and they just need to be displayed. With SVGs, you have real-time rendering, and you shouldn't overuse them. If you have something that's like more than 100 nodes inside of the SVG, you have to consider using raster image. This is a thing that you probably need to discuss with the designers in your team to see which works best. But the rule of thumb here is that you should always try to make the web page much easier and much simpler in any way. Another example of this is, again, image with mask and pre-cut image. Both look the same to the end user. And if you don't plan to change this in any way at runtime, for example, to have some kind of a animation that moves the picture around or something like that, you don't really need a mask. If it's just an avatar image, you're pretty much okay with having your designer pre-cut it in Photoshop and just have it with a white background baked in. Another example of this is box shadow and filter shadow. Filter shadow actually respects the alpha. What we talked a bit earlier about here, that there is a phase that the mask is analyzed. Filter shadow respects that, which makes its computations much more heavy. So if you just need to create a shadow-like effect, you can use box shadow for rectangular figures. You don't need filter shadow. Filter shadow you only need when you have more complex shapes with alpha mask. And again, if it's just for the shadow and it's not going to be animated or changed in any event during the lifetime you're in your app, you can again consider just creating an image for this. But it really depends on the use case. Another factor in rendering performance for your apps is what kind of animations do you use. This has been a long topic for many years, which is the best way to do animations. Is it through JavaScript? Is it through CSS? If it's CSS, what kind of CSS? Are there transitions or the timeline the best option? Basically, still there's no silver bullet for this. It really depends on the particular use cases. But in general, if you have simple animation like pulsing or something like hover or something that's animating just a couple of properties, it's just much easier to have it as CSS animations, either them being timeline-based or transitions. If you want, of course, more complex things like keyframe animations with complex easings that are running for a long time with different animated properties, it's much easier to control this through JavaScript because it's just too complex to handle with pure CSS. But again, when you use JavaScript, you can use two important things. Request animation frame, which basically allows the browser to render what you want it to render as its next frame. It's not like set interval or set timeout where you have dumb counter that counts when this happens. It allows the browser to optimize when this rendering is going to happen. So basically this says, hey browser, for whenever you're drawing the next frame, please do this. And another innovation in the last couple of years is the Web Animations API, which basically allows you to have much finer control over animations from JavaScript. And one more thing, of course, avoid long-running input handlers, especially for mobile, like touch end, touch start. To have them running for a ton of time, it's really not great because it blocks rendering. You can again use request animation frame here to just offload the handling of whatever you want to change. And one last thing, if you're really interested into the browser internals and how they look, work under the hood, you can actually use Chrome tracing. Just type Chrome tracing in your browser, and basically you'll see all the internal processes that are actually running inside of the browser. And you'll be able to really see all the different things that we were talking about and the different subprocesses that are related to that. So a couple of takeaways. Basically, rendering, the actual rendering is the visualization of your web page. The earlier you go back into the rendering process, the more expensive are the changes that you're making. And in general, just try to keep your DOM, CSS, and JavaScript simpler. So thank you.